Okay, today we are talking about a research direction that there's actually going to be quite a couple of videos coming out in the next near term set, specifically because this is actually a direction of research that I myself was involved with, as we will see in future videos. In addition, I might make some more introductory videos on MCMC methods, but for now, we're going to briefly motivate this problem of Markov chain Monte Carlo, but not go into depth on sort of the basic introductions. I might do that in another video. There's probably there is a lot of content already online introducing people to these sort of methods, so I'm not sure if I have much to add to that selection, but we'll see. But for now, what I want to get into is basically uh, this paper from 2022 called Quantum Enhanced Markov Chain Monte Carlo, a follow-up work and some implementations, of course. And so to begin with, let's briefly remind ourselves of what the goal of Markov Chain Monte Carlo methods are. Basically, in this setting where we have access to some sort of potentially unnormalized log probability function, or as many in the physics community would call it, an energy function. We want to sample from the distribution that it describes. So, for example, here they have a sort of canonical example in physics, which is the Ising model. And so there's a lot of ways you'll see it come up, or names you'll see it come up, like spin glass models and things like that. But basically, it's a discrete probability distribution. So an Ising model, there's lots of ways to think about it. Can be thought of as a graph or sometimes a lattice, right? But it's a collection of binary variables, which you can call spins, or you don't have to call spins, which are parametrized by an energy function that has this J, which is a sort of interconnect matrix. Basically, J would be 0 if these spins have no influence on each other. Otherwise, dictates how correlated the spins are, basically, right? So if J is positive, then you can see here, right, the spins are either +1 or -1. So if the spins are the same thing, then this energy, right, we want to be at a minimum. And so this energy will be minimized if J is positive and these two are the same values. So you can see J being positive here would mean that these two variables are correlated, and J being negative would mean they're anti-correlated. And so that's just a comment on a way to interpret this. And H here is just sort of a bias term that's applied to each individual site. And so the energy function, right, is describing this unnormalized log likelihood. You can see basically somewhere they probably write it out. They do not actually, but basically you have this, here it is, you have this Boltzmann distribution, which is e to the negative energy, and T here is just temperature in an abstract sense, and divided by a partition function, which is, in the case of binary variables, a sum over all states, and a sum over the sort of exponential of the energy over all states. And so in the continuous space, right, this is just an integral over the state space. And this ensures that basically it's a normalized probability distribution. Now, in general, if we have, right, like an Ising model that we can represent on a computer quite easily, we can say it's, an n by n matrix is our J matrix. It could be pretty big, right? We could have 1,000 by 1,000 matrix or something. That would be totally tractable to compute the energy function of. But if we wanted to compute the partition function Z, we would have to sum over every possible state, right? And we can see that the number of states grows exponentially, right? Because we have, it's sort of in a very quantum sense, we have two possible states for each spin, and then right, every spin we add on doubles the number of states we could have in total. So if we have 1,000 states that we want to sum over, or 1,000 spins, then that becomes very intractable very quickly. And so a lot of times, right, the whole goal of this sampling process is to draw samples from this distribution so we don't have to actually compute z, the partition function. And so that's the motivation here. Going into it, I realized that if you're not familiar with MCMC methods or this approach, that was probably very quickly, but maybe we can get into more detail in another video. But for now, we're going to be moving on. So with this in mind, the question at hand is basically, there's a lot of traditional methods to do this, both old school, right, like all the way back to the 40s and 50s when the Metropolis algorithm first came out and it was refined in the 70s by Hastings, who added this correction to it for non-symmetric proposals, to all the way up to today. There's still ongoing research. You can find papers regularly in machine learning and physics journals even about sampling. And so this is obviously a continued area of research relevant to a lot of things. Anything you probably want to do actually in machine learning has a lot of connections to it. Drawing samples from distributions that we don't have access to a true distribution, but some log probability of is very common. And so one thing that is important to keep in mind is that this is what's motivating the quantum. So in the quantum case, right, the question is basically, so we have these in general methods for sampling from this distribution that we'll see right here. Basically, right, this is sort of the Metropolis Hastings algorithm, is that if we have some state S, we propose state S prime with some probability function, right? This is just Q is called our proposal function. And then we either accept it or reject it. And the intuition here, right, is in the case of symmetric proposals, what that means is that you are equally likely to go from state S to state S prime as you are to go from state S prime to state S. So, right, a canonical example of that would be a uniform random sampling algorithm, right? If you say, I'm going to, every time in my discrete space, I'm going to randomly pick a set of binary variables or binary flips, and I'm just going to do that, then that would be a example of a symmetric proposal. Non-symmetric proposals would be something that might depend more actually on the current state, right? If you say, okay, I'm going to, for example, in the case of like continuous sampling, you might say do some sort of Langevin type sampling where you say, okay, I'm going to look at sort of the gradient of my energy at this state. And the gradient is obviously different depending on what state you're on. And so in that sense, the proposals might be symmetric or asymmetric. And so what we have in most of what we'd be talking about in this paper will be symmetric. So we can, in general, sort of ignore this Q. With that in mind, the question is now basically, this algorithm is great, except you want to do this as efficiently as possible, right? Like you can do this in uniform random probability sampling, and it'll converge provably in the limit of infinite samples. But of course, we don't want to wait infinite time. So how do we do this more efficiently, right? Especially in larger state spaces. And the answer is basically almost always we want to do a better proposal function. That's where a lot of research goes into, is saying how do we do a proposal function that is better than just random or some sort of local step change. And that's what this paper is, right? The question is, how do we do sampling? And how do we do sampling specifically by accelerating it on a quantum computer. So what can quantum computing offer to MCMC methods? And of course, the reason, I guess I didn't get into this, maybe we'll just talk about why it's called MCMC in another video. But anyway, so the question is basically, what can quantum offer? And the basic idea, to summarize it very briefly, is that we can use a quantum computer to do a quantum simulation that will inform the proposal function. And basically, we prepare a state and we sample another state from a quantum computer. And if we are potentially smart about how we set up this quantum circuit, then we might be able to compute sort of advantageous proposals. And so the basic idea here is that you can see in the first figure is basically that you would consider a couple varieties, right? You could have a local update where you might say, okay, my new proposal has to be something like a Hamming distance 1 away from my current proposal, which restricts you. It's still a valid MCMC algorithm, but it just restricts sort of the rate of change, right? If you look at this distribution, it'll take a long time for you to realistically get over to the other side of this middle hill. Uniform is good. You can jump all around, but there's no information guiding you, right? You are literally just jumping around at random. So you have information on acceptance or rejectance, but you don't really have any information about like where you're going. And the idea is that the quantum, you can sort of provide information about the problem to the quantum circuit, and ergo use that information to propose better states. So getting into it, basically, right, we're just looking at this proposal function. And the intuition here is just that, right, we want mu here, just looking at their notation, right? Mu here is just this probability. And so we want the probability of the new state to be greater than the probability of the old state. And so when that happens, right, we want to increase this. You'll notice though that it's right probability divided by probability. You might think, wait, I thought we were doing this whole thing so we don't have to compute mu, right? Mu is hard because that's a partition function, but these two terms share the same partition function because it's a global function over all states. So it cancels out, and this is just the difference basically in the energies. So yeah, moving on, basically, I've summarized a high level, like, what do we have to do? Well, we have to sample from a Ising model, and we want to do it using a quantum computer. So how do we do that? That is the question at hand. Well, it's actually not too hard. In all honesty, basically what we do is we say, we have the quantum algorithm here. So it's simple. We say if the current configuration is S, basically we just prepare that into a basis state, right? Because we have a binary representation. So we need a sort of linear number of qubits with respect to the number of states. And then run a proposal unitary, which is symmetric, right? This is why we can drop the Q term here, is because it's symmetric. And then classically read out the state from a single sample, right? And jump to this new state with this probability. And so that's the whole algorithm. Now, of course, the real meat is what do we do for U here? If this is just like, right, if this is just a sequence of Hadamard gates, then we just have recovered our uniform sampling algorithm. And so the idea right here is that what we want to do is that we want to pick a smart U. And the way to do that is to actually evolve the Hamiltonian of our system. So what we have here, right, is H probability is the actual Ising model that you see here. That is just the energy function of the Ising model, of course, over each state that we are doing an evolution here. Now, of course, the Hamiltonian itself is a time-independent Hamiltonian. This is energy function does not depend on time. And so basically what this does is it encodes the classical problem, and then we have in a very QAOA type manner. In fact, there's some follow-up work on sort of QAOA type proposals for quantum enhanced Monte Carlo methods. We have this mixing Hamiltonian, which can help basically generate quantum jumps or transitions around this problem. And we just have a parameter that controls the strength of it. And so basically, your mixing Hamiltonian, right, can be anything. It doesn't really matter as long as they're symmetric. And the problem, though, is that if the mixing Hamiltonian was this really complex thing to compute, then it would be not ideal necessarily, because you would be able to have difficulties on simulating or running this computationally. We have basically experimental difficulties, but regardless of the advantages or disadvantages that a dense mixing Hamiltonian would provide, they do go with a very factorizable mixing Hamiltonian, which is just, this is very classic, right? You see this all the time in sort of QAOA type approaches, which is just a sum over the poly x on every qubit. And so then they also have this just a normalization that is in alpha. Basically, this just normalizes over the this f. It's just the Frobenius norm of each of these matrices, which can you can show is actually efficient to compute. And so this is quite easy then, in some sense, right? We have two Hamiltonians that do not commute that we are going to simulate, and then that's going to be our proposal. So we can basically do a trotterization here for simulation, which is a very classic approach, right, in quantum computing. So all they do here is, instead of doing any optimization, right, on how to evolve it or anything, they just do a random trotterization, right? So they randomly pick sort of the weights here and the time to simulate of their trotterization at each iteration. And so that's all there is to it, right? You basically randomly trotterize your problem with a mixer, and then you evolve it in time, and then you draw a proposal, and there you go. And so moving on, we can look at the actual performance. And in this case where we have discrete proposals, we can analytically just compute the transition matrix. This is not true in general, of course, but in pedagogical cases, in cases in which we can actually simulate the quantum system, of course, we have access to the actual matrix itself. And so if we look at that, we can basically just look at the spectral gap, which is just a difference in the eigenvalues of this transition matrix. And the idea here is that the spectral gap, which describes basically 1 minus the maximum eigenvalue that isn't 1, basically describes the slowest decaying state if you do this spectral expansion. And so by looking at that, you can see sort of the rate of convergence is the idea. And so where, of course, this spectral gap being 0 and 1 describes the slowest and fastest, because that 1 minus eigenvalue of 1 means it would sort of immediately decay. And so that's the basic idea for their analysis. And so what we see here is, depending on the temperature of the equation, right, where e to the negative e energy over t and T here is the temperature. So high temperature, right, means you're dividing by a large number. Low temperature means you're dividing by a small number. What that means is that there's a substantial difference oftentimes in difficulty between sampling at high temperatures and sampling at low temperatures. At low temperatures, right, you can see because you're dividing by a very small number, things become a lot more sharp. And what do I mean by sharp? I mean, if you literally look at the plot like just a Gaussian energy function and you decrease the temperature, right, the well gets sharper, which means oftentimes in sampling, right, it can be harder to escape that well. So low temperature sampling is definitely hard. At, of course, infinite temperature sampling, then naturally that this is just a uniform distribution that you're sampling from. And so what we see here, right, is that we want, as we can see before, we want the spectral gap, this absolute spectral gap, I guess, to be 1. Like higher is better in this figure. And so what we see is that for these low temperature updates, the quantum computing proposal does substantially better than some sort of uniform proposal or a local proposal. And so I would guess the reason the local proposal does so exceedingly poorly that it's not even shown for lower temperatures is simply because imagine, right, at low temperatures it becomes an extremely sharp landscape, which means locally, right, if you take one step, you're basically, if you had like this first figure, right, and this was a way sharper, right, and you had a local step, you would basically almost never take that step because it's such a high increase in energy that you would never really almost have a 0 probability of accepting that step practically. And so it takes an extremely long time to converge. And so that's basically the idea there. It's just showing that in the limit of lower temperatures, the quantum proposals can provide a lot of potential improvement. And this is for n equals 10 spins. And we can see as the number of spins increase that the rate of decay in terms of the spectral gap is much better for quantum proposals than it is for the uniform or the local proposals. And so what they do here is they show the convergence experiment, basically just what we saw above in terms of the spectral gap. And then what they do is they actually run it on some of the IBM quantum systems to see how experiments converge with the theory. And we see that experimentally, interestingly, that the spectral gap is worse at lower temperatures and better at higher temperatures. And my, uninformed guess would be that this is because the quantum experiment is closer, right, in general at low temperatures and high temperatures to the uniform random proposal, because you are less like the theory and more like the random uniform because of the effect of noise, basically. And so that's just, we just see, this is just a chain that we see there, and this is just the convergence basically of a Markov chain over time. And the interesting thing about this work and this direction is basically 2 things. One is that it's very not reliant on variational tuning, right? A lot of, as I've talked about before, there's a lot of difficulties that come with variational methods, and this is not variational. There are, at least in this initial method, no parameters to learn. And so that does have some appeal, and it can be very fast on, for example, superconducting devices. This is right, something that you're executing very quickly, which is important for drawing lots of samples. And the other benefit is perhaps that it is pretty robust to noise. I suppose in the sort of traditional worst case, right, where it's like, okay, my circuit just is so deep, it just becomes literally like uniform random noise, then you sort of have your worst case being what the classical algorithm is already sort of doing that you're benchmarking against. So in that perspective, it is sort of better to do this in quantum in many cases. Now, if you have correlated errors that, right, then your worst case is not uniform random, but might have some bias, in which case that's not as good. So just something to keep in mind, but definitely robust to noise could be interesting as an advantage for sort of pre-fault tolerant hardware, because it is, as we said, right, like this is just drawing a random proposal. It's not expected to be 100% accurate 100% of the time, because even like literally there's just shot noise, right? We're drawing a single shot, and so that's important to keep in mind. And so that's basically the idea of that paper. You can see there's a lot more in the appendix, but that doesn't really matter for us. And so what are we talking about next? Well, what is the actual potential speed up of this? And the TLDR is that sort of worst case, there's no speed up. That doesn't seem too intuitively surprising, right? This is sort of reliant on the quantum simulation being better than randomness. And our quantum simulation is probably only better for certain kinds of problems. You wouldn't expect to just universally have one sort of problem encoding that you could always do things better. And so there's a lot of sort of construction that you could do that you would potentially not have this perform super well. That being said, it's always good to prove the limits of these methods, and we can see in this paper, which I'll link, that in general the worst case is that there's no speed up over classical methods. So this is where it's sort of a very practically reliant algorithm. It just depends on, right, if you can actually get a speed up or not. That's what matters. And so what we have next, of course, is an implementation available in this code base, which I will link below. Basically, it's in TensorFlow probability, and the idea is to just, and TensorFlow quantum, and the idea here is that we have this Ising kernel only supports 1D Ising models currently, so that's obviously a limitation, but right, we have this circuit that we build, and then every time we parameterize it with random trotterizations, and then we draw a sample, and we say that is our next state, and then we of course accept or reject with a given probability. This is just a classical Ising model proposal, right, where we just have a uniform proposal function, and then we just wrap it in a Metropolis Hastings correction, and that's our sort of algorithm. And it's quite simple to implement, right? In TensorFlow Quantum, we just have the sort of binary variable that we're encoding. Then we sample once from the trotterized circuit, and that is our next state. And then we can look over here in the example folder, and we can see sort of the creation for a variety of different random J and H parameters that we're providing. And we basically just plot the post burn-in sort of energies. You can see it's not really showing much of note for a smaller system size, but as we get to larger system sizes, you can see some potentially interesting energy advantages. Now, obviously, in the limit of infinite iterations, these will necessarily converge, but in the limit of very small iterations, they may not. And so this is potentially highlighting some relevant convergence properties of the quantum enhanced Markov chain Monte Carlo. So as always, the code and papers will be linked below.